My name is João Paquete Ferreira. I'm a biochemistry master student from FCT Nova. And first of all, I'd like to thank to the organizing committee for the opportunity to be here today presenting some of the work I've been developing for my master thesis. For my master thesis, I've been working with a bacterial protein that is associated with biofilm formation. Biofilm is a bacterial growth phenotype characterized by the bacteria growing attached to themselves and enclosed in a self-produced polymeric matrix. This phenotype is associated with infections in indwelling medical devices, leading many times to the failure of those devices, and also to persistent and chronic infections as bacteria lose their susceptibility towards antimicrobial agents when growing in this phenotype. As bacteria are a lot less susceptible, the antibiotic doses need to be very elevated to try to eliminate the biofilms, and sometimes it's impossible to do so. To understand the best approach to eliminate biofilms, we should know how a biofilm is formed. So, to form a biofilm, we start with planktonic cells, and these will start adhering to a surface and to themselves in the stage known as the initiation stage. After this, the biofilm will maturate and gain its final structure and size. The biofilm is then maintained through programmed cell death mechanisms, and dispersal of the biofilm allows cells to come back to the planktonic phenotype, and it is a quite problematic part, as an infection that was once localized can become widespread through the dispersal mechanisms. As the bacterial cells become highly resistant to the antimicrobial agents when in the biofilm, the best approach is to target the initiation stage, as this stage is the one where the cells did not get yet the resistance. For the initiation stage, teichoic acids are an important part. Teichoic acids, there are two types: the wall teichoic acids that are attached to the peptidoglycan, and the lipoteichoic acids that are anchored in the cell membrane. Generally, they have a topology that comprises a linkage unit and a main chain. The linkage unit is made of disaccharides and a small chain of glycerol triphosphate, and then the main chain is made up of several different repeating units that can be glycerol triphosphate and orbital phosphate, as this is the most common. The biosynthesis of all teichoic acid starts inside the cell, and the linkage unit is the first part to be assembled and is assembled attached to a lipid carrier. Then the main chain is biosynthesized, and here, depending on the repeating unit present in the main chain, two different pathways are followed. Once the polymer is completely assembled, it is translocated across the cell membrane, and once outside the cell, it's attached to the peptidoglycan by the LCP family of proteins. This step is very interesting to target as it occurs outside of the cell. It's easier to inhibit as a molecule that is the inhibitor won't have to enter the cell to exert its effect. So I'll go into more detail regarding the LCP family of proteins right now. So LCP stands for LITAR, CPSA, PSR. There are three types of proteins that belong to this family of proteins, and they have a general topology that comprises an intercellular N-terminus, a transmembrane domain, and the LCP domain that's extracellular, and it's highly conserved among these proteins, and it has the phosphotransferase activity responsible for transferring the wall teichoic acids to the peptidoglycan. Some of these proteins replace these two parts with a signal peptide. In my case, I'm working with the litar of Streptococcus dysgalactiae, subspecies dysgalactiae, that contains a short signal peptide, the LCP domain, and what we believe to be a glycan binding domain at the end of the C-terminus. However, I'm working with a protein construct that contains only the LCP domain and a small his tag at the end of the C-terminus to help in the purification process. Why am I studying a protein of this bacterium? This bacteria is known to cause bovine mastitis. It's a disease that's characterized by the persistent inflammation of the mammary gland of the cows. It's a highly impacting disease for the dairy industry, as it might be potentially fatal for the cows and might contaminate the milk with bacteria or some toxins released by the bacteria during infection, rendering the milk useless to human consumption. My main objectives are the determination of the first three-dimensional structure of the lethal protein of this organism, and then characterize the interaction of the protein with putative ligands. Regarding the crystal structure, the protein crystallization was done using the vapor diffusion method, and we used as precipitating agents ammonium sulfate. The data collection was done at the ESRF at the beamline massive 1, and here are the statistics of data collection. We were able to collect data that diffracted until 2.8 angstroms. To solve the structure, I used the molecular replacement method. The space group is the I422, and for this I need to use an ensemble, and for that ensemble I found out that the best one was used for superimposed homologous structures that I'm depicting here, and as you can see, the general topology of the proteins it's the same with slight changes in the structures. Here now I'm at the final stages of refinement. Here is the structure at the current refinement stages. Then I superimpose the structure with a homologous one from Bacillus subtilis containing a bound substrate, and as you can see, the general topology of the proteins is really close. Here I'm depicting the conserved residues that are important for the activity of these proteins. There are the two aspartic residues and the arginine residues that are stabilizing the pyrophosphate group. The aspartic residues are stabilizing the magnesium ion that is also very important for the activity of these proteins. In terms of biophysical characterization, we start with the thermal shift assay to find out what was the best solvent where we can dissolve the compounds as they were not water soluble, and as you can see here, we choose the DMSO as the melting temperature of the protein is not highly affected by the presence of 10% of this solvent. We also studied the interaction of the protein with the following ligands, yet we found out that this technique was not suitable as these ligands are highly hydrophobic and mask the signal of the melting temperature of the protein. So we changed to the circular dichorism. This technique allows us to study the secondary structure of the protein by doing a spectrum in this array of wavelengths, and as you can see, the spectrum doesn't change much in the presence of the MSO, and then when we did it in the presence of the ligands, you can see that it seems that the protein regains the native spectrum, which is a good indicator of that some interaction with the protein might be happening here. Then we did then we did thermal ramps, and as you can see, the changes in the melting temperature of the protein are really small, so we cannot conclude binding from this assay. So the main conclusions I can retrieve so far was that I was able to solve the structure of the protein and that it has a high structural homology with a homologous structure with an RMSD close to 1. And in terms of biophysical characterization, the MSO does not seem to destabilize the protein, and this technique is not suitable for studying protein-ligand interactions. And then in terms of the CD, the tested ligands don't appear to bind. It might be true because of the technique, it's not sensitive enough, or binding is not happening at all. And as future work, I want to obtain a higher resolution structure and test more interesting ligands and explore other techniques. Thank you so much for your attention.